So today what we're going to talk about is motion, and what's going to be really important about this is that it's under constant acceleration, or we also say uniform acceleration. And I want to pull up three different equations we're going to use in order to figure this out, okay? To make the equations a little bit easier, all right, instead of x sub f for the final position, we're going to use just x, all right? So whenever you see x, that's really x sub f. You're also going to see v sub f. Instead of the final velocity, we're going to use v. And then also instead of t sub f, we're going to use just plain old t. So the final ones are going to be t, v, and x. And just realize that those are going to be the final ones, okay? All right, so here what we have is a position time graph, and we have 2 points on it. This one right here is on the y-axis, so the time is 0. And the initial position, we're going to still call x sub 0. And so some time went by, and now this point right here, the x coordinate, the horizontal coordinate, is going to be t, our time, and then our final position, which is going to be x. All right, so what we're going to do is we're going to figure out the slope of this, because if you find the slope between 2 points on a position time graph, what you get is the average velocity, okay? So this horizontal change, we went from x sub 0, or not x sub 0, x sub o to x. So this change is x minus x sub o for the original, okay? And then this horizontal change is going to be t minus 0, which winds up being just t. So we know from previous lessons that the average velocity is the change in position, so x minus x sub 0, over the change in time, which in this case would be just t. All right, so now we're going to multiply. So now we have this equation, and its average velocity is displacement over the time. And we're going to multiply both sides of this equation by time, which on the right-hand side, the time is going to cancel out. And so we have the average velocity times time is equal to x minus x sub o. And then I'm going to add x sub o to both sides. So I get x sub o plus the average velocity times time, and that's going to equal my final position. Okay, so this is going to be a big equation. So my final position I can figure out by taking my initial position and adding my average velocity times my time. And that's one of the equations that we are going to need. So for this next graph, we have a velocity time graph. So this is the velocity. And what I want to point out to you is that the slope is acceleration. So the slope of a velocity time graph is acceleration. Now, the slope is the same for any 2 points on here, which is telling us that the slope is always the same value. So the slope is constant, okay? Which means we have constant acceleration. So if we graph the slope, that would be a horizontal line. So that's how I know it's a constant acceleration, okay? In this case, the average acceleration and the acceleration are going to be the same. So we know that instead of writing a bar, we're just going to write a. Okay, so since this is velocity, this is the original velocity or the initial velocity, and this is going to be at time times 0. So this would be 0 comma v sub o for original velocity or the starting velocity, and this point right here is going to be t comma v for the final velocity. So I'm going to draw my slope triangle in here. Okay, so then this would be this horizontal change, or not horizontal, vertical change would be v minus v sub o. So right here, v minus v sub o. This horizontal change would be t minus 0, or just t. Okay, so instead of writing a bar, right, average velocity or average acceleration, we can just write acceleration this time. Okay, and you can always do that when the velocity is a straight line like this. Okay, so a is equal to our slope, right? So that'd be v minus v sub o over our change in time, which is t. Very similar to what we just did earlier, okay, with the position time graph, okay? We can wind up getting the final velocity out of this by multiplying both sides by t, and then that would give me a times t is equal to the velocity, the final velocity, minus the original velocity. I'm going to add the original velocity to both sides, so this becomes v sub o plus at, acceleration times time, would give you the final velocity, or v is equal to v sub o plus at. Okay, so this is going to be a second equation that we need. Okay, so we have the final position is the initial position plus the average velocity times time. The final velocity is equal to the original velocity plus the acceleration times time. So I know that x is equal to x sub o plus the average velocity times time. I also know that the average acceleration is equal to v plus v sub o divided by 2. I also know that the final velocity is equal to the original velocity plus the acceleration times time. So these two were from the first page, and this is what we just came up with, okay? All right, so what this means is this V bar, okay, and you know what, I'm gonna write this differently. I'm gonna write it with the 1/2. So I'm gonna change this so that V bar becomes 1/2 times V plus V sub o. Okay, so how is that helpful? Okay, this is helpful because right here, this V bar and this is V bar, they are both average velocities. So this average velocity right here can be replaced with the 1/2 times V plus V sub o. So I'm gonna take this and replace it with this because that's true because they're both average velocities. So that means that x is equal to x sub o plus parenthesis, and so this V bar, this average velocities, becomes 1/2. Actually, I don't, hold on. Let me start again with this. I just didn't like the way I was writing it, okay? So this V bar becomes the 1/2 V plus V sub o. I had an extra set of parentheses that I didn't need, that's why. Okay, so 1/2 times V plus V sub o, and then times the T. Okay, so I'm just using color coding to help you see it. So I took this V bar and replaced it with 1/2 V plus V time, 1/2 times V plus V sub o. All right, so now what I can do another substitution because right here, I know what V is. So this V right here is my final velocity, right? It's the final velocity. Well, that's also the final velocity. So this is gonna allow me to replace this V right here with V sub o plus AT. All right, so here we go with all the colors. Okay, so this is gonna become X is equal to X sub o plus, and then the 1/2 parenthesis, and then that V right there becomes V sub o plus AT. And then plus the V sub o. And then multiplied by the T. Okay, hopefully you can see all the color coding with this, okay? So now what we can do is just mathematically clean this up, okay? Because we have a V sub o here plus another V sub o, that makes 2 of them, right? So this becomes X is equal to X sub o plus 1/2 times, and this becomes 2v sub o plus the acceleration times time. And then times another time out here, okay? All right, now you could do this a couple different ways, but what I'm gonna do is I'm gonna distribute this t with each of these, okay? So now this becomes x is equal to x sub o plus 1/2 times 2 times v sub o times t plus a times t, or that'd be at squared. All right. Now, what I'm going to do next is I'm going to distribute the 1/2. So I'm going to multiply this by 1/2 and this by 1/2. So that gives me x is equal to x sub o, and then 1/2 times 2 is just 1. So this becomes plus v sub o times t plus, and then 1/2 times this at squared would just be 1/2 at squared. So this equation is important because what it does is it relates for us the time of movement, okay, the acceleration, the original velocity, the original position, and the final position. And you can move stuff around and solve for one of these if you know all the other ones. So there's 1, 2, 3, 4, 5 different unknowns. There's x, x sub o, v sub o, t, and a. If you know any 4 of those, you can solve for the 5th one, okay? All right, so this is the equation x is equal to x sub o plus v sub o times t plus 1/2 at squared, okay? And this is important. The acceleration is constant. You can't use this if it's not. Acceleration is constant. Or we also say it's uniform acceleration, okay? So that's important. You can't use this if the acceleration is changing. If it's always the same number, you can use it. Like if the acceleration is always 2 meters per second squared, you can use this formula, okay? So here's the 3 equations I'm going to use, right? We already saw this one and this one and this one, okay? This one I'm going to rewrite as v bar is equal to 1/2 times v plus v sub o. This one, this time I'm going to write it, I'm going to do something a little bit differently, okay? I want to solve for v sub o, okay? So if I solve this for v sub o, I need to subtract the at from both sides. So this becomes v minus at, because I subtracted at from both sides, is equal to v sub o, okay? Or v sub o is equal to v minus at. All right, so we're going to do something very, very similar to what we did before, okay? This v bar right here, well, what can I replace it with? I can replace it with this, okay? So I'm going to start with x is equal to x sub o plus, instead of v bar, I'm going to write 1/2 v plus v sub o, and I'm going to color code it again. So 1/2 v plus v sub o times the time. Okay, so last time I replaced v. This time I'm going to replace v sub o. So this v sub o is going to get replaced with v minus at. All right. So now I have x is equal to x sub o plus 1/2 times v plus, and this part becomes v minus at. And I'm going to close parenthesis and multiply by t. Okay, so that v sub o right here got replaced with v minus at because they're the same thing. It's all substitution from like math 1 and math 2, okay? All right, now the next thing I'm going to do is I'm going to remove the color. I'm just going to do the algebra on this now, okay? I just want you to use the color to help you see where everything's coming from. So right now, I can combine v plus v. That'd be 2v minus at. So inside the parenthesis here becomes 2v minus at. So x is equal to x sub o plus 1/2 times 2v minus at times t. All right, now I'm going to distribute the t. So x is equal to x sub o plus 1/2 times 2vt minus a t times t would be t squared, so minus at squared. Okay, now I'm going to distribute the 1/2. So x is equal to x sub o plus, well, 1/2 times 2vt becomes just vt. So vt minus, and then 1/2 times at squared would just be 1/2 at squared. Okay, so this equation we can use if we know 4 of these. If we know the final position, we know the original or starting position, we know the final velocity, we know the time, and we know the acceleration. Okay, so if we know any 4 of those, we can find one of the others. Okay, and that's the whole idea behind this. Okay, now once again, this was all based on this, and both of these are based on the acceleration being that the velocity graph being a straight line, which means the acceleration is constant, right? So here, x is equal to x sub o plus vt minus 1/2 at squared. And we can only use this. This is what's really important, if the acceleration is constant. So when I took physics, let me write this because I can't talk and write at the same time. All right. When I took physics, nobody stopped and said, hey, you can only use this when acceleration is constant. I wish somebody had. I would probably have understood it a heck of a lot better. Okay, so here's another equation. Okay, and then we have one more to come up with. So this time we're going to use, once again, x is equal to x sub o plus the average velocity times time. And the average velocity is also equal to the final velocity plus the original velocity divided by 2. All right. And then, okay, then we have this one, right? So I'm going to actually use it in this form. Okay, so I'm going to write it in red. V bar is equal to V plus V sub O divided by 2. We're going to use that one. And I'm just doing this for color coding. Okay. Now, this time, what I want to do, and you're going to see in a minute why, okay, is, well, actually, let me start this, okay? So I'm going to, sorry, I changed my mind how I was going to do it. All right, so right here, x is equal to x sub o plus, okay, now instead of v bar, I'm gonna replace this v bar right here with v plus v sub o divided by 2. So I'm gonna put that in parentheses. So v plus v sub o divided by 2. I'm gonna close the parentheses here. You're gonna see in a minute why I'm leaving it like that, okay? All right, now I have this time right here, right? Because this v bar is being multiplied by t. So this is the same as the average velocity, right? So I need to multiply that by my t that was right there, okay? All right, now one more thing that I need to do, okay? Over here, I can replace this time, okay? Now, how can I do that? This time right here is the same as this time right here. So what I'm going to do is I'm going to subtract v sub o, and I'm going to use a third color. So I'm going to subtract v sub o from both sides. So that would result in v minus v sub o is equal to the acceleration times time. Because I'm multiplying by acceleration to get the t by itself, I could divide both sides of this equation by the acceleration, and I would have v minus v sub o divided by a is equal to my time. So what does that allow me to do? That's going to allow me to take this time and remove it and replace it with v minus v sub o divided by the acceleration. So this winds up being x is equal to x sub o plus, and I'm going to leave the color in here, v plus v sub o divided by 2, close the parenthesis, and then this t gets replaced with v minus v sub o divided by a. Okay, so now these are two fractions. So what I can do is multiply the numerators together and multiply the denominators together, okay? So that would result in x is equal to x sub o plus, and then the top would becomes v plus v sub o, that quantity times v minus v sub o, all over 2 times a, which is 2a. Okay, now the next thing I can do is multiply this. Hey, from Math 2, you know what we can use? We can use the area model to multiply it out, and that's exactly what I'm going to do. Okay, so I'm going to do 2 by 2. The top is going to be v plus v sub o. This side is going to be v minus v sub o. And so v times v is v squared. V times v sub o is positive v times v sub o. V times negative v sub o would be negative v times v sub o. And do you guys realize this is a difference of squares? You might, okay. And a positive times negative is going to be negative. And then this is going to be v sub o and squared. So I like to put parentheses around this v sub o when I'm squaring it, just to show you that you're squaring the v sub o. Otherwise, it looks like 0 and 2 on top of each other, and I don't want to quite show you that, all right? Okay, so back over here, this can be replaced with v squared minus v sub o squared, because these two cancel each other out. So this becomes x is equal to x sub o plus v squared minus v sub o squared all over 2a. Now this is a little bit of a cumbersome equation, so what I'm going to do is I'm going to move the x sub o over to the other side, so I'm going to subtract it from both sides, and you wind up with x minus x sub o is equal to v squared minus v sub o squared all over 2a. And so I don't want any fractions in my equation, okay? So what I'm going to do is I am going to clear this denominator out by multiplying both sides by 2a. Now, to multiply this whole side by 2a, I'm going to have to put parentheses around this, okay? So this is going to be 2a, and let me slide it up a little bit so you can see it. 2a times x minus x sub o is equal to, when I multiply this side by 2a, well, I'm dividing by 2a, and I'm also multiplying by 2a, so those are going to cancel, and I'm left with v squared minus v sub o squared. And then what I'm going to do is I'm going to get this v squared all by itself, so I'm going to add v sub o squared to both sides. So that would wind up giving me v sub o, slide it up some more again, v sub o squared, because over here it's minus, so over here it's going to be adding, and then plus 2a times x minus x sub o is equal to v squared. Or the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times x minus x sub o. Okay, now what's important about this is, notice there's no time involved, huh? So this is going to be an equation that's going to be really important when we don't have time, but we have the starting velocity, we have the acceleration, and we have the final position and the initial position. We can use all that, okay? Once again, this was all based on, I'm going to slide it up, based on these two equations, and these two equations were based on constant acceleration. So once again, we can only use this when we have constant acceleration, okay? So constant acceleration, I think I said last time I said acceleration constant, same thing, okay? Constant acceleration. All right, so what we have now are 5 different equations, okay? that we can use for final position, and original position, final velocity, original velocity, acceleration, and time. All right? So going over all these motion equations, and I want to put them all together on one page so you can have them and you can pull this up and look at it when you start solving these problems, okay? So the very first one is we know that x is equal to x sub o plus the average velocity times time. We also know the final velocity is equal to the original velocity plus the acceleration times time, all right? And then we also know that the average velocity is equal to the final velocity plus the original velocity divided by 2. And then we know the final position is equal to the initial position plus v sub o times t, the original velocity, okay, times time, plus 1/2 the acceleration times time squared, okay? And then we also have final position is equal to the initial position plus the velocity, the final velocity times time, minus 1/2 AT squared. All right. So this one right here is missing V. So if you have V, you don't want to use this one, okay? This one right here is missing the original velocity. All right. And then we have another equation that tells us the final velocity squared is equal to the initial velocity, the original velocity squared, plus 2 times the acceleration times x minus x sub o. So what this one is missing, okay, you're missing t. You're not given t, and you're not trying to find it, okay? And also up here, I didn't do these off the get-go, okay? But this one right here, this very first one is missing the acceleration. So it's missing A, and then this one is missing an X. Okay, and what I'm gonna have you do is I want you to list everything you know and then also what you're trying to find, and that's gonna help us pick which equation we need to use. So with this first problem, okay, we have an object with an initial velocity of 4 meters per second. Okay, so you gotta kind of read this and understand it first. Okay, so let's just go through and read it and then pull stuff out, okay? It moves along a straight axis under constant acceleration. Okay, so that right there tells us we can use all the formulas, okay, that we've developed. 3 seconds later, its velocity is 14 meters per second. And then how far did it travel in this time? Okay, so going through what is known, okay? Okay, so what's known is the starting velocity, right? The original velocity or the initial velocity. So that's V sub O, and that's 4 meters per second. Moves along a straight axis with constant acceleration. Okay, so we know it's constant, but they never told us the acceleration, right? They're not telling us that. 3 seconds later, okay, so that's t equals 3. And then that would be seconds. Its velocity is 14 meters per second. So that's at the end of something, right? So that's going to be the final time. And so our final velocity is going to be 14 meters per second. So V is equal to 14 meters per second. Okay. And then how far did it travel in this time? Okay. Now, something else, when we start this, we want to know how far it travels. So we're going to start the initial position at 0. And then when we get our X, that's going to allow us to know how far it traveled, okay? So we're trying to find X. That's what we're trying to find, okay? And so let's write find x, right? So you're given everything but acceleration. So I'm going to flip my paper and go back to the page that we just did, all right? And if you look at this, all right, we can't use this bottom one because it deals with acceleration. We can't use this one because we need acceleration. We can't use this one because it needs acceleration. This one doesn't have acceleration. This one has acceleration, and this one, okay? So these two right here, now this does me no good by itself because I don't have that x, right? I don't have x in it. So I'm gonna wanna use this one, right? So I'm gonna use x is equal to x sub o plus v bar, right? The average velocity times time. Okay, so I know the time is 3. I don't have my average velocity, but I'm also going to use this, the fact that my average velocity is equal to my velocity plus my original velocity divided by 2. And that's this one. So I actually have to use these two in conjunction with each other, okay, together with each other. All right, so v bar, okay, the average velocity is going to be my velocity, which is 14 meters per second, okay, plus my original velocity, which is 4 meters per second, and then divide by 2, okay? So that's going to give me an average velocity of 18 meters per second divided by 2. So that gives me an average velocity of 9 meters per second. Okay, so now I can use x is equal to my original position, which I know is 0, and I should have put meters on this, okay? 0 meters plus my average velocity, which I now know is 9 meters per second, times my time, which is 3 seconds. Okay, so then my final position would be, this would be 0, and this comes out to be, you know, my seconds cancel here, and I'm left with 27 meters. And I want us to round to 2 significant figures, and it comes to us already with 2 significant figures, so we're done, okay? So since we started at 0, right, since the position was 0 at time equals 0, then this right here tells us how far it traveled in this time. So it traveled, okay, the object traveled 27 meters. Slide it up. Okay, so the object traveled 27 meters. That's what I meant to show you. Okay? All right, let's go to the next example. So we're designing an airport for small planes in this problem, okay? And one kind of airplane that might use this airfield must reach a speed before takeoff of at least 27.8 meters per second, which is 100 kilometers per hour, okay? And it can accelerate at 2 meters per second squared. So this is the acceleration, okay? And because it's given to us as a number right here, it's constant, okay? If the runway is 150 meters long, okay, so we're gonna start this where the plane takes off, we're gonna start this at 0, and then we're gonna make our final position be 150 meters, okay? So we need that distance, that start to finish, to be 150 meters, okay? And when planes take off, okay, they start from stop, okay? They start from a dead stop. So that means the initial velocity is 0, okay? So for part A, here's just some things that we know, okay? What's known. All right, so we know that V sub O is equal to 0 meters per second. Okay, now that is not the final velocity. We're trying to figure out if we're gonna make that velocity. So we're gonna check it against this one, okay? Because we want it to be at least this. So we're trying to actually find if this is all works out after 150 meters, will that velocity be bigger than this, okay? So we wanna find V, okay? That's what we're trying to find. All right, now what else do we know? We know the acceleration is 2.00 meters per second squared. We know at the end, okay, we know our initial position is going to be 0 meters, because that's where the plane starts to take off at, okay? And we know our final position needs to be this 150 meters. All right, and then we also know from up here, the acceleration is 2.00 meters per second squared. All right, so I need something that I don't, now notice, I wasn't given a time, right? I wasn't given a time. So I'm probably gonna wanna use this one. Okay, so here's my final velocity, that's what I need. If you look at this, okay, I want it side by side. Okay, if you look at this, all right, I want to figure this one out. I know this one is 0. I know my acceleration is 2. I know this final position is 150, and my initial position is 0. So I'm going to use this one, okay? So that means v squared is equal to v sub o squared plus 2 times 2.00 meters per second squared times 150 meters minus 0 meters, okay? And I want to round this to 3 significant figures. So on these problems, in fact, probably from here on out, on homeworks and stuff, I'm going to probably be giving you and telling you how many significant figures to round to, okay? So now it's just a matter of, okay, so this was 0, okay? So v squared, I actually should have put 0 there to begin with, okay? V squared is 0 squared plus, and we could do some cleaning up here. This would be 4.00 meters per second squared times, and this cleans up to be 150 meters. And so v squared, well, 0 squared is 0. So this turns out to be 600 meters squared over second squared. So this is 600. And because we have meters times meters, that's why I'm saying meters squared over second squared. And then I'm going to square root both sides. And when I square root this, guess what happens? I get meters over seconds. So my velocity turns out to be, when I put this into the calculator, okay, so I'm going to grab a calculator. And it turns out to be the square root of 600. And it turns out to be 24.495. Well, I'm going to write them all out. Okay. So V turns out to be 24.49489743 meters per second. Now I asked you to round to 3 significant figures. So here's my first one. Here's my second one. Here's my third one. I got to look at the fourth one, which is a 9. That's going to cause this one to be a 5. So my velocity is 24.5 meters per second. And the question was asking, is it going fast enough to take off after 150 meters? And how fast does it need to go? It needs to go 27.8 meters per second. Is it going 27.8 meters? No, it's only going 24.5. Okay, so can the airplane reach the proper speed to take off? Okay, no. The plane will not be able to take off if the runway is 150 meters. All right. So, okay, if not, all right, and this is going to be part B. Actually, let's pause for a second here. So for part B, if not, what minimum length must the runway have? And we want to round our answer to 3 significant figures, okay? So this time we want the velocity. We're going to see, okay, how long does it need to be to reach this velocity, right? Because we need to make it a little bit longer, right? And we need this final velocity to be 27.8, okay? So I'm going to slide this up a little bit. Actually, I'm gonna stop this. Hold on a second, guys. All right, for part B, what is known and what am I trying to find? So this time I'm trying to find x, and what's known is my initial velocity is 0 meters per second. My final velocity must be 27.8 for it to take off. I know my initial position is 0 meters, okay? And I know my acceleration is 2.00 meters per second squared, okay? So back to finding the equation that fits, right? Okay, so which one can I use? Well, actually, I can use this one again, because here's what's important. Here's the giveaway is I haven't been given a time in this, right? How long does it take to reach this speed or anything like that? Or it takes 5 seconds. There's no mention of time in this problem, right? And so this is the one you're gonna wanna use when you're missing the time, okay? So we're gonna use the same equation again, all right? So we have v squared is equal to v sub o squared plus 2 times a times x minus x sub o, okay? So putting everything in, this is gonna be 27.8 meters per second squared. So 27.8 meters per second squared is equal to 0 meters per second squared plus 2 times my acceleration, which is 2.00 meters per second squared times my final position. Well, that's actually what I'm trying to solve for, right? So this is going to be x minus x sub o. Well, that's going to be 0 meters, right? Okay, so you don't want to, I'm going to tell you this, you really don't want to do any calculations. You want to bring everything together, okay? So unless it's going to be 0, like this one's going to be 0, we don't have to write that, okay? So cleaning this up, this is 27.8 meters per second squared. My point is you want to put this all in the calculator at the very end, okay? So you don't have rounding error, okay? So this is 0 squared, so we don't need to write it because it's just 0. And this becomes 4.00, so equals 4.00 meters per second squared times x minus 0. Well, that's just x, right? So all I need to do is, to get x by itself, is divide both sides by this 4.00 meters per second squared. All right, so 27.8 meters per second squared divided by 4.00 meters per second squared is equal to my x. Now, what are the units for this x? Well, it's going to turn out to be meters, okay? So my x is going to be equal to, and you just put it all in your calculator, okay? So I'm going to do a fraction bar here and parentheses, 27.8, close the parentheses, and then squared, and then divide by 4.00. And we get 193.21. And this would be meters. Okay, now I asked you to round this to 3 significant figures. Okay, so let me slide it down. Round your answer to 3 significant figures. Okay, so 1 significant figure is the 1 here. 9 is the second significant figure. 3 is the third one. The fourth one's a 2, so we're going to keep this at 193 meters. So x is 193 meters, okay? So the minimum length of the runway length is 193 meters. All right, guys, and that's motion problems, okay?